In this lecture, I will discuss the basics of serial communication and specifically how to set up serial communication on the PIC 16F1719 microcontroller. Serial data communication is commonly used for a variety of applications, and it allows us to send a single bit, one bit at a time, across a data channel. This is commonly used for a variety of data that is transmitted over networks, data transmitted to peripherals, and all sorts of communications within and between computer systems. And so what will happen is you will typically have a single line to receive data, a single line to transmit data, and the data rate is managed by a clock. In some cases, there is another pin that is an external clock that is used to clock the data through, and in other cases, data is simply transmitted and on a data bus at a specific rate of speed set by a clock manager. And we will only be allowed to send one bit at a time, but that will be done very quickly. So much of modern peripheral communication, modern internet communication is done serially, largely because processors have gotten so fast at sending data. Previously, in older technology that you may have seen in the 90s and early 2000s, you would have seen more parallel communication. So if you've ever seen old printer port cables that were thick and wide, those were parallel ports. If you've ever seen IDE cables for hard drives that were wide and connected to ribbon cables, those were parallel communication. Modern day communication, serial communication, is so fast that we can send things one bit at a time and do just as well shifting things into a shift register as we used to do with parallel communication. It's important also to understand the term duplex. So systems can either be full duplex or half duplex. And what full duplex means is that you can both send and receive at the exact same time. So an example of that would be a modern day telephone. You can speak and you can hear at the same time. Sometimes that means people can talk over each other, but you can both hear sounds and transmit sound at the same time. Half duplex systems are only capable of either receiving or transmitting at any given time, and so you have to switch back and forth between modes. So an example of that would be a walkie-talkie, where if you push the button, then you are able to transmit a sound across to the other walkie-talkies in your system. But at that same time, when you are the one who is transmitting, you cannot hear the incoming signal from others. So you can only have one person transmitting at a time, and the others are in receive mode only. USB is a very common application of serial communication, and this involves many modern day peripherals. So the USB was developed in the mid-1990s, and Intel was one of the first companies to use the USB standard, and they used them in 1995. It started in 1996 with the USB 1.0 standard. Just like anything else, we want to have various standards for our communication. That way, if you buy a USB mouse or a USB printer or something like that, then you know that it will work on anything that takes USB. You don't want to have one that only works on Lenovo systems and another that only works on Dell systems and another that only works on name your favorite manufacturer's systems. So those standards govern how fast data can go. They govern the pin orientation and how these ports are arranged. So USB 1.0 was fairly low speed. They had both a low speed and a high speed mode. So the low speed mode could operate at 1.5 megabits per second in terms of data transmission rate, and then the full speed mode could operate at 12 megabits per second. Now it is important, as we're talking about data speeds, to differentiate between megabits and megabytes. And so a lot of times when we think about file size, we think about things in terms of bytes, megabytes, gigabytes. A lot of times for data rates, they're talking about megabits. So your cable company or whoever your internet service provider is will discuss things in megabits per second. That way things sound 8 times faster than they really are, because you have 8 bits in every byte. In the 1990s, there was some development into the 1.1 standard, and that was really when you saw the first widespread use. That was when a lot of commercially available computers started carrying at least one USB port. USB 2.0 really gained traction in the early 2000s, and that significantly enhanced data rates. So we went from low speeds in the mid-90s of 1.5 megabits per second up to 480 megabits per second, and then in the later part of the first decade of the 2000s, we started seeing USB 3.0, and the first devices that used those emerged in 2010, and that allowed for 5 gigabits per second, and that standard has since been enhanced to allow for 10 gigabits per second. So that allows really rapid data transmission. USB 2.0, which you can tell is a 2.0 device if you look at the port, and it is a black port on the back of a computer, has 4 pins. There is a 5 volt and a ground, and that is why you can charge things using a USB device. So those 5 volt and ground not only provide a reference for the serial data that is coming across the channel, but they are also used by a lot of modern day devices to charge things like batteries on cell phones and other low current batteries that need to be charged. They have 2 data pins. One is data minus, the other is data plus, and you can see on the slide screen the colors of these wires. If you were to ever cut open a USB cable, you would typically see your 5 volt signal is red, your ground is black, and your your data are white and green. Sometimes the data minus is blue, depending upon who's manufacturing your USB cable. And so the data plus and the data minus actually carry the same data, but one is just the complement of the other. And that allows us to still send data in one direction at a time, but the redundancy is for error checking. So if at any point your data minus signal and your data plus signal are showing the same polarity, either they're both logic 1 or logic 0, that indicates that there's an error in your transmission. But if you're seeing that one is the exact opposite of the other, that is the normal operating procedure for a USB. USB 3.0 actually added more pins, and that allows for simultaneous or full duplex simultaneous send and receive. And it is backwards compatible with USB 2.0 devices, so if you have devices designed for USB 2.0, you've probably found that they can still fit in a USB 3.0 port. You can tell you have a USB 3.0 port because it has a blue color inside of the port on the computer. And those added pins allow us to have more simultaneous data transmission. Serial ATA, or SATA, is used inside of most modern-day computers for their hard drive systems. And these create a single bus of data and allow data to be transmitted from the hard drive to memory and other locations on your computer. So SATA emerged in 2003, version 1.0, and it had a data transfer rate of 1.5 gigabits per second. And the latest standard available is version 3.4, which came out in 2018. That allows for 6 gigabits per second. This is typically for internal transmission for internal hard drives, but eSATA is also used for external hard drives. So you can get an eSATA external hard drive, and that allows for rapid data transmission to your hard drive. Serial communication with a PIC can be done in a variety of modes, and in this course what we are going to use is what is known as the USART, or the Enhanced Universal Synchronous Asynchronous Receiver Transmitter. And you can read a lot more about this in section 31 of the data sheet, beginning on page 354. Throughout the rest of this lecture, I will break down the various registers associated with that, what those different bits do, and how we can set up for both serial transmission and serial receipt of data. So this is a block diagram that shows the transmit portion of the USART. And so in this case we have several things that are happening here. On the bottom left-hand side, you will see that we have the baud rate generator. So the baud is actually determining the speed at which data is transmitted through. And so there are various registers associated with computing that transmission speed. TXEN is very important. That is the transmitter enable. So if you are not enabling that bit, then you cannot transmit any data. And then what happens is when you're ready to transmit data, you will use the TXREG. That is the register where you are going to set up the 8 bits that you wish to transmit. You can also do 9-bit mode, and so that comes in down here if you want to send a 9th bit, but we will use 8-bit data transmission. That goes into the transmit shift register, and what happens in the shift register is those bits get shifted out, starting with the least significant bit, and then 1 bit at a time just goes shoo, 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 and gets shifted out to the TX pin. Now, of course, the TX pin needs to be set up as an output, just like any other I/O pin would be. And you can also use an interrupt with this. So when the transmitted data is sent out, you can set this flag, TXIF. That is one of the flags in the peripheral register, PIR, and you can enable an interrupt there. So when you have completed a transmission of data, you can trigger an interrupt as desired, so you can handle that once the data is transmitted. The data will come out the TX or the CK pin, and so that is part of port C, which we'll talk about later. This is the block for receipt, and very similarly, we have similar baud control. You want to make sure when you're sending and receiving data that both ends of that channel operate at the same baud rate, so the data that's received comes in at the same speed as the data was sent out. You have an RX pin, which is used for receipt. We need to enable the serial port to be able to pull that data in, so SPEN has to be enabled. CREN is for the continuous receive enable, and then the OERR is part of error checking. So if there was an error in transmission, you will see that flag will come up. And in this case, the data is coming in across this pin. It comes into the RSR, which is the receive shift register. So you have the transmit shift register on sending data, you have the receive shift register on receiving, and then this data is coming in 1 bit at a time, from least significant bit to most significant bit. And then finally, once all 8 bits have come in, then that register gets moved over to the RC1 register. That's where you can pull it in. If you did send a 9th data bit, which we will not, but if you chose to do that, then that would be put in the RX9D bit, and we can use that as well. Again, this can also trigger an interrupt, so the RCIF flag will indicate when the data has come in and is ready for receipt, and you can enable an interrupt associated with receipt of data. So if you wanted to handle this in an interrupt service routine, you could do that. So let's talk about breaking down into the various control registers and what will need to be set up and how those registers work in a little bit more detail. So baud rate can be controlled in a variety of ways. There's multiple formulas that can be used depending upon how you want to configure it. You can either use an 8 or a 16-bit control on the baud. We're going to use 8 bits, and if you are using 8 bits, that means we will clear the bit BRG16. So BRG16 is a bit that indicates whether you're using 16-bit baud rate generation control or you're using 8-bit. We will use 8-bit, so we won't need to set BRG16. And that is in a register baud 1 con for the baud control. Here are the formulas. We are going to be using the asynchronous mode, so we are going to primarily concentrate on the top 4 rows in this table. And so there's the sync bits, there is the BRG16, which we just talked about, and then there's the BRGH. And so sync is determining whether we're using synchronous or asynchronous mode. We're going to use asynchronous. And then the BRG16 is determining whether you're using 8-bit or 16-bit baud rate control. And then BRGH determines basically which of these formulas on the right end of this table we're going to use. And so that determines whether you're going to divide the frequency of oscillation by 64 or by 16. So this allows us to choose either higher or lower baud rates depending upon whether we have a 0 or a 1. So if we put in a 0 in BRGH along with BRG16 and sync, then our baud rate is determined as the frequency of the oscillator divided by 64 times n plus 1. 1. And n plus 1 comes in these SP1 BRGH and SP1 BRGL registers. That is a pair. If you're using 16-bit mode, then those two registers get put together as a full 16-bit control. And since we will just be using 8-bit mode, we will only be using the value in the SP1 BRGL. So whatever value you put in there, that is the n that is used to divide this on down in the denominator. So if you were to just put 0, 0, 0, you would be in 8-bit asynchronous mode, and the formula for your baud rate would be FOSC divided by 16 times n plus 1. The frequency of our oscillator will depend upon whether we have enabled the 4 times PLL that is on board our PIC. So if we have disabled that, we will use a value of 8 megahertz or 8 million, and if we have enabled that, we will use 32 megahertz or 32 million in those calculations. The data pins that we will use for serial communication are part of port C. So TX is on RC6, RX is on RC7, and of course we will need to set up things as outputs and inputs. So the transmit will need to be an output, the receive will need to be the input, and then we will also use the RC6 PPS to configure RC6 for use of the TX pin. So this is very similar to what we just found out in the motor control lab when we needed to make sure that the PWM bit was set up in the CCP1. So this RC6 PPS register does allow us to use the TX pin. So we will make sure that that is set appropriately. The TX1 STA register is an important register in terms of how this transmit of data will occur. And so this is basically just the status and control. So it tells you a little bit about how things have gone, and it tells you about how you are going to be transmitting data. Bit 7 is a don't care in asynchronous mode, so we won't worry about that. TX9 determines whether we're transmitting 8-bit data or 9-bit data. We're going to use 8, so that bit will go to 0. And then bit 5 is our transmit enable, and so in order to transmit anything, we will need to make that a 1. If we are going to be on the receive end, we will make that a 0. And then synchronous, the sync bit, determines whether we are in synchronous or asynchronous mode. We're going to be in asynchronous mode, and so we will set that to a 0. And then send B allows us to send a break between our data. We're not going to use that, so we will just set that to a 0. And then the BRGH we already talked about is involved in whether you're using high or low baud rates. And then TRMT is a bit that determines whether the transmit shift register is empty or is full. And so that just tells you a little bit about how things are going with the transmission of data. And the TX90, if you were to be sending a 9th bit, that would be where you would hold that as you're shifting things on out. We won't be worried about that, so we'll just put a 0 into that bit as well. When you do set up the data to be transmitted, TX1REG is where you're going to put the data that you want transmitted out. So what will happen is you'll put a value into TX1REG, then that will be copied into the TSR, which is the transmit shift register, and that value will be sent 1 bit at a time from least significant bit to most significant bit across the TX line. So it will just take the least significant bit, send that out, send the next bit, the next bit, the next bit, and all of that will be sent at the rate set up by the baud rate control registers. RC1REG is where you will actually receive the data back. So on the receive end, that will be where the data will come in, and that will be held until you pull it back out and put it into a variable of your choosing. And so that will be very important to use as you are on the receive end. So the order of operations, you can find a nice itemized list on page 357, that is section 31.1.1.7 in your data sheet. This talks about how to set things up for transmission. So you will need to use the registers we discussed and the bits we discussed to set up the baud rate that you want. You will have to enable the serial port to be in asynchronous mode, and so in order to do that, you'll need to set SPEN and clear the sync bit. So clearing sync puts you in asynchronous mode, setting SPEN enables serial ports, and then you'll have to set up for 8-bit mode. We're going to clear the TX9 bits, so you can simply say TX9 equals 0. You're going to enable your transmission with the TXEN bit, so just say TXEN equals 1. That enables the transmission. And then whatever value you want to transmit, you're going to put into the TX1REG register. And then once everything is set up, you can simply just keep putting in the values in TX1REG 1 byte at a time as you wish to send those on out. And so you will just send and send and send and send for all of the bytes that you wish to send. Now it's important that you pace these things, so you can either watch the flags to determine when things are done, or you can put in a delay and just make sure that you're waiting long enough between transmission that you don't have a problem. The receive is very similar, so you can find a list of how to configure the receive starting on page 361, which is section 31.1.2.8 of your datasheet. The baud will be set up the exact same way as you are on the transmitter, and then you'll want to make sure you've cleared the Ancel C bit 7, so RX pin is in digital. It'll probably be a good idea to clear bit 6 for the TX pin as well. And so then we will enable the serial port. In this case, we also need to have SPEN. So whether you're transmit or receive, you need to clear SPEN, or sorry, set SPEN and clear SYNC. So we will set SPEN to 1 and clear SYNC to make it asynchronous. We're going to clear the RX9 bit. That way everything will stay in 8-bit mode. And then we're going to enable continuous receive of data. So just setting CREN, that allows us to continuously receive every byte of data that comes through. You can enable the interrupt if you want to have an interrupt service routine to handle the data, or you can simply poll. And what we will do is simply poll for that data. And then what we will do is wait for the data to come in. And so you see on the screen what we can put there is while exclamation point RCIF. Exclamation point is short for not. So while the flag is not set, meaning the data is not there yet, we're just going to have a hard wait. So that's what the semicolon there means. It's just while that we're going to do nothing other than wait until RCIF is set. Once RCIF is set, then the data is ready and we can pull it in from the RC1REG and put it into whatever variable that we want for processing.